It is open now.
Okay. Okay, ladies and gentlemen, dear colleagues, as President of the Landesarchiv Baden-Württemberg, I'm delighted to welcome you to this workshop. The Landesarchiv Baden-Württemberg is the state archives of the German Bundesland Baden-Württemberg, a higher state authority with 8 departments at different places all over the state. Our work and leading principles are based on 3 columns. Firstly, we are a service provider for the public administration, following our legal mandate to secure and preserve official documents. Secondly, we offer information on the history of Baden-Württemberg to anyone interested in many different ways. And last, but certainly not least, we see ourselves as an integral part of research infrastructure. But now let me move on to the focus of today's workshop. Our society, economy, science and administration depend on databases. And ever since databases are introduced in the 1960s, data has been lost due to neglect or lack of know-how. But only 1 decade later, in 1970s, the very first archivists started to preserve database content for future generations. We at the Landesarchiv Baden-Württemberg have now been archiving database content for nearly 20 years, beginning with census data. One of the first datasets we received reaches back exactly 60 years to the year 1961. There is, however, a big difference between merely preserving data and making it usable. We made great progress in making those data comprehensible in 2006. This is the same time we started developing a software for database preservation, making the archiving process more efficient and well documented. The software is called DMAC. We have since shared our software as well as our knowledge on database archiving with colleagues, especially with our partners in the DMAC development group, and we will continue to do so. With DMAC, we and 200 other archives in Germany, Austria, and Switzerland have committed ourselves to design and implement software for ingest, storage, data management, access, and preservation planning of digital-born objects. Today, our database holdings comprise registers with nearly 300 million items on census data, but also subjects as diverse as road construction, criminal justice, environmental data, and data from museums. This may already seem like a lot, but there is still a huge gap between our goals and our current means. A great amount of government activities has not yet been appraised and transferred to our long-term archive, mainly due to missing support by the government departments and agencies and a lack of standardized ways to extract database content. In all those years, we have kept observing the technological progress in the area. All in all, we have to note that the challenges grow and we are eager to improve the more or less still basic capabilities we have so far. We count on the outcomes of this workshop as an input for strategic decisions on database archiving in the next year, both at the Landesarchiv and in the DMAC development group. We will, of course, be happy to share its outcomes with the worldwide community. All presentations will be made available as video recordings, and there will be a written report as well. I would like to warmly thank all presenters, minute takers, and discussion hosts for the share they take in this workshop. Also, thanks for the technical support to my colleagues at the Landesarchiv, especially Wolfgang Kraut and Patrick Leiske, and everybody else involved. And last but not least, thanks to Kai Naumann for preparing this workshop in an effort that first started in April last year. I wish you all the best for your presentations and fruitful discussions. Thank you very much for your attention.
I'd first like to point out what is a database from my point of view, and what you might share. Firstly, there's a graphical user interface layer. Then that is what the user of the database sees. Then there's a business logic layer, a database management system layer, and then there's a storage layer. And there you'll have the database and maybe also large objects connected to the database. And if you take up examples for that, you'd have a web browser, PHP, MariaDB, and Linux. Or you will have the C-hash GUI library, the C-hash programming language for the application, DBase data files, and a CD-ROM. It all depends when this database was conceived and how it was implemented. In fact, technology has really grown a massive web of varieties of databases. This is the genealogy of relational database management systems I found in my research. It all started in the 1970s, and ever since stuff has forked and it has been fused as well. It's really confusing. This is just an outtake of the whole genealogy that Hasso-Plattner Institute has published. There has been research on that issue, and it started already quite early. The concept of time went into consideration already in 1983. And 20 years later, the idea of using XML for database archival emerged, or at least that date 2003 is what I found in my research of literature. And then in 2007, it was really institutionalized via the CEART format and its related tool, which is now called the CEART Suite. And also a first international workshop on database preservation had been held, the PresDB 2007 in, I think, Edinburgh. And in 2013, we've seen CEART emerge as a Swiss national standard. And also in 2013, some guys pretty closely related to one of our presenters, Klaus Rechert, did a proof of concept for database preservation through emulation. There'll be more milestones, especially the efforts that some people also inside this community in this workshop have done so far. This is on E-ARK and on the idea of establishing CEART as an international standard as well on the European level. Or I think we'll find out about what you are doing right now on that task. So I didn't mention it because it's not yet finished, but I think I really appreciate it. You all know about that challenge that I started in April 2020. In fact, as we already pointed out, the results were not too solid, but we've got we could set up some solutions, 5 solutions, 2 responses. Then we also derived ideas from literature and some advice given during conferences. The CSV solution, the XML solution, doing disk images and reviving them via emulation, also doing this via Docker images, and then a hybrid solution, which said, well, please set it up on a website. So that stuff has to be public data, and alongside that also store it in a special format. What in my research was guiding me as well was the question of efficiency and the cost associated with keeping data for such a long time. And I set up this cost projection chart, which started in January 2020 and ended in January 2080. And that was my view of how cost might evolve. But we don't have any reliable data on that. And I think this is just an impulse for what we'll do during the workshop. So that's what has been done up to now.
For philosophy, and the DCH was the Data Center for the Humanities, where I was a speaker for 6 years, and also the CCH, which is the Cologne Center for Humanities. And within this context, we had a DFG project called Sustain Life. And out of this project, we had this panel at the DH called Sustainability Strategies for Digital Humanities Systems. And the first question that I want to answer is, why is sustainability even an issue in the digital humanities? And well, the obvious reason is because when you ask digital humanities scholars, as we have done in 2016 and 2018 as well, this is a top problem that they see, that there is no maintenance of the website after the end of the research project. So this is a general research data survey that we asked this, and this is apparently what people thought would be the most pressing issue in digital humanities. The other thing that we did was we looked at lifespans of digital scholarly editions. If you want to know exactly how we did that, it's a little complicated how you measure a lifespan of a digital object. What we did basically, we took a registry of digital scholarly editions and then measured how long they were available as far as we knew. And one of the resources that we used, for example, was the Wayback Machine. So we had this little graph, and depending on whether you see a straight line or the beginning of an exponential curve, we have two measures for you here. Either that's 8.5 years on average or 6 years half-life. As I said, depending on how you feel about this particular curve. And for a humanities scholar, this is actually a very short amount of time, because they tend to think in terms of books, and a book, yeah, I mean, you can just throw a book in the corner and come back 200 years later, and it's still a book basically, and it will still be somewhat readable. So yeah, this is a bit of a paradigm shift for many scholars in that area. So, and also, like, what is a digital scholarly edition? I mean, I can assume that many of you have never worked with something like that. And it's a book with annotations, but unlike an actual book, it's online. And there are a couple of things that are special about that. First of all, the DSE, I picked that here because it's fairly typical for humanities projects. They are online somewhere, they have a lot of text, but they also have a database, which is why I'm here presumably, or some sort of XML data storage where the actual information is placed. The text is to be displayed and how these are interlinked with other things like translations. Additionally, there are also interactive components, which is something that Kai did not mention, but which for us is actually very important, because how good is a database if you can't search it, if you can't work with it, if you can't run the analysis that you want? Maybe the interactive components are even more important than the data itself. So this is also something that we have, and that are somewhat many digital scholarly editions have these components. Also visualizations, also very important. And these are like the typical, the complete package, which makes it extremely hard to preserve, to say the least. And yeah, and that's very, very often the situation that we have, is that we have a combination of data, of representation, and also of digital services. And then we're supposed to sustain that indefinitely for no money. So how do we do that? I will present a couple of projects here and some basic strategies, which are actually kind of similar to what Kai said earlier. One of them is that we try to make cheaper maintenance by bundling project. The Sustain Life project that I talked about earlier is in the direction. It's also the GAMS, which should be noted here, which we also do a very interesting thing there. Then there's the idea that when you have a legacy project, that means something very old, you can always just, make it again and make it again as something that's more sustainable. And this I will present 2 projects that follow this strategy. Then there is the sandbox, which is actually just a part of what the King's Digital Lab is currently doing. And then there is also the web archiving, which has already been mentioned as well. And just to clarify, first of all, why these particular projects, and also how am I involved with these? We did have a panel at the DH 2020, which didn't really take place due to Corona, as you probably heard about Corona. So if you see the author list, it's color-coded now, and you see also the projects that are also color-coded now. We didn't have anyone from the Internet Archive, but I hope it will become clear why I added that as well. Just, as full disclosure, I am not personally affiliated with most of the projects that are presented here, and if I may, I got the information from them last year, so I am not 100% sure that it's still accurate. And if I give my opinion, it's my personal opinion, not necessarily those of the people and projects involved. Thank you very much. Okay, let's start with something where I can, talk quite open about, and that's the Sustain Life project. Our goal was to increase sustainability of complex living systems, such as these digital scholarly editions. And the method that we use is to meta-mold the components in Tosca. Tosca is an open standard. The goal was there to streamline maintenance processes, for example, allowing us to update multiple services once, restart systems automatically, and very, very important, do updates and tests automatically. So basically, when the system fails, we know, and then we can restart it. And if and there's a new, it can be updated with a notification, and then we do the update, and the update fails, and then we roll back to the old version, make a little note that it didn't work, and so on and so forth. And a lot of that is more or less automatic, and the Tosca system really helps with these processes. What we currently have is 5 active prototypes, which are right now maintained with very little work. And what we learned from this was that we can use this actually fairly easily on legacy projects. So we had some, the prototypes were basically more or less randomly chosen, had a wide variety of technologies, Java, PHP, and all kinds of servers and operating systems and whatnot. And we were able to capture these and describe these components very easily. And well, not me, but the person who worked on the project. And we also did a study with students where we figured out that they could learn that and apply that fairly easily as well. And yeah, and it does improve maintenance costs quite significantly. So before that, we usually had like almost 1 person for each of the projects, and now we basically don't have anyone, just more or less do that on the side. But what we also found out is that inevitably a redesign or shutdown is necessary, because at some point the components become just so outdated that we cannot put them on the internet without posing severe security risks to ourselves and our servers. And at that point, we just have to give up. So a colleague of mine did a bit of a joke that we are kind of like a hospice for living systems. We put them there and we give them nice drugs and make them very happy. And occasionally we just shut down small components, amputate an arm or so. And at the end, we put a nice tombstone where they were supposed to be, or make something new. I admit a lot of these metaphors are very morbid, but I will go on like that. Okay, this is one of the prototypes. And again, this is where we shut down a couple of the functionality, but mostly the back end, which we don't really need anymore anyway, because that was where a historian was supposed to put in all the data. And since there's no more historian to put in the data, we don't need the back end to facilitate that. Interesting enough, yesterday when I wanted to do that screenshot, the system was down due to maintenance. So I had to give them a call, like, I need that for the screenshot. But there it is. So it was really quick. The second project that I wanted to present was the GAMS, which is also a very different approach. And the idea there is that they were a little unhappy that in the digital humanities, basically everyone uses their own technologies and their own software, and then nothing is compatible with each other, and it's really hard to keep all this zoo of technologies together to make decent sustainability strategies. So they say, okay, we need to step away from that, and they create the GAMS, which is a modular standards-based software that projects can use to implement the digital assets, which will then be maintained through the central system. So basically, it's a center and quite a lot of people working there. And so everyone who's doing digital humanities in Austria basically goes to them and says, okay, we have this and this project in mind, and how can we do that with your system? And they go like, okay, please do it like this. And since the system is very powerful, that works quite well. The current state is that they have much more than we have in the Sustain Life project, which is 95,000 digital objects and over 90 projects. The lesson that they learned, at least when we talked about it, was that it only makes sense when you catch people from the very beginning. So the project we did in Sustain Life, that we took projects that already existed and try to revive them in some way. This is not their approach. They go like, okay, we really need to be there with you from the beginning, or you can kind of have to start over. And but what they have, and what's apparently very valuable to them, is that they have the support of the funding agencies in Austria, that they say like, okay, you're doing a digital project, maybe you want to look over there. There's another problem that sometimes they cannot get together with the projects because their project needs that cannot be accommodated, but that's apparently very rare. And then people have to find other solutions for sustainability. And of course, that there's the issue that, which is also a nice side benefit, that sometimes a project benefits from features that have actually been implemented for another project, and so retroactively the projects get better and better without anyone doing anything. You do need strong ongoing funding for such a center, otherwise it doesn't work. I mean, if they were to shut down, I don't think anyone could save these 90 projects. This is in parentheses because this is like a remark that is from my personal experiences, is that this type of really large system and the complexity that they have is really challenging to manage. So you really need to be on your toes to not get the feature creep and the code dead in your way, and try to keep it slim but also powerful, and that's really challenging, and to do that over a long period of time. They have done it, so I have no complaints, but it's something that you really need to be on your toes for, and it can go horribly wrong. This is how this looks like, and I basically only have to show this one because it all kind of looks the same. So, but I think it's actually kind of nice, also from the usability perspective, because lessons that have been learned for one digital edition can then be used for other digital editions. So, this is actually a good thing to have these sorts of lessons that can be transferred between projects. Then we had the University of Victoria, who also had a similar problem. They were asked by the university leadership to sustain a humanities project that have been built inside the university. And they thought, okay, maybe, well, I think we should just keep it simple. That's really their motto. In case you don't know the acronym, there's an S missing that I omitted. And their method is that all the legacy projects are redesigned to use just HTML, CSS, and JavaScript, and that's it. Oh, okay, I really need to hurry up here. And so the idea is that they are comparatively stable and they can live on a USB stick and have low maintenance. They have over 10 projects right now, and what are the lessons? Very low is not zero. It's quite suitable for legacy projects, but it's much cheaper if people build it with that technology stack from the very start. And what they also found is that although that doesn't sound like much, they can actually do almost anything that they wanted to do in the past. So they don't need anything more than that. This just to illustrate just how flexible this is. This is both done with the same system. Lazarus project. There we basically just try to revive 3 projects. What we found there and the lessons learned is that once the project has stopped and the person who was responsible for the project, the last person who was responsible for the project has left, going back and trying to recover that is really, really difficult and very costly, and you have to do something that we like to call data archaeology, which is very yeah, it's very expensive in many ways. And if you tell that to an archaeologist, they're not surprised, because you know restoring a Ming vase is much more expensive than buying one in the, I don't know, 11th century or whatever. Yeah, this is pretty much the case. So the cost of the restorations were actually quite a lot higher than the original IT costs. One of the key lessons that we learned is you never promise to keep something running unless you have seen it firsthand and up close, and have tried to make it run by yourself. Yeah. This is how that would look like. One of the things that they also did was transform data to XML and add a little bit of a search engine and so on and so forth. But I mean, it worked, and all 3 projects are running strong. King's Lab at King's College, their goal is how to archive over 100 legacy projects without funding. What they came up with was basically a 6-option tiered thing. And well, option 1 is just give us a lot of money and we will just re-implement it and everything will be fine. But I think the interesting ones are the one on the bottom, where they basically say, okay, we will just take your system, we put it into a virtual machine, and we have a placeholder website, and then we look for maybe any web archiving that has been done, and then we put on the link, and that's it. That's like the tombstone variety or strategy. And they currently have 31 projects in that lowered option, over 100 in total. And yeah, one of the main problems is that both virtual machines and web archiving are not available in web search. So you need some way around that if you want your project still be relevant in the modern world. One thing that I thought was really, really interesting is that they just put in the projects and published it as research data, which was quite interesting. This is how that looks like, very minimalist, and yeah, you can write them an email basically and ask them for the virtual machine, and then you get this little page here to, let people know that this still exists. And this brings me to the Wayback Machine. Their goal is to archive the internet. You probably heard about that. If you haven't, check it out. It's really, really cool. And they're very open to archive all our stuff, mainly because it's both digital cultural heritage and digital research, which is something that they both are very interested in. However, once it's in there, it's not in Google, so you can't really find it, and it might be broken. In case you haven't seen it, this is how it currently looks like. And this is how that project that I showed earlier from King's College looks like. And this is where the map should have been, but it isn't. So be prepared for that. So conclusion, and I have 2 more minutes. I've been doing good. Okay, my conclusion is that it's a challenge, and the ideal situation is that you redesign everything every 7 years to keep it fresh, and also to keep it with additional to keep it up to date, to make it look beautiful, because beauty standards, if a website is 7 years old, you can see it because it's just not as pretty. There are a couple of what I call shoestring options. One of them is web archiving, and the other one is static HTML. Basically, just put it out there very raw, very uninteractive. You can do that with or without JavaScript. JavaScript makes it slightly more complex, but the nice thing about JavaScript is it tends to be fairly compatible. However, not all projects can be transformed in such a way without loss, and you have the problem that while your resource might be in theory archived, it's invisible and therefore might not exist anyway. So this is a bit of a problem. There are some ways to go around that by, for example, have these tombstone pages, as we have seen. And of course, what is highly recommended and what we now do fairly regularly is to take the data and archive that. Now, ideally in at least 2 venues, and also to have code also archived. So in theory, people can replicate it. But of course, that's just a theory. We know that in order to actually do that, it's very difficult. I really love the King's Lab approach with all the layers. It's basically what we wanted to come up with, but they did it first. And I also think that if you are in a system where something like GAMS exists, then you should definitely consider joining it, because there are so many synergies between these different projects that it's definitely a plus to do that. Okay, and that's my quick overview of the digital humanities and how we sustain our digital resources. I believe there might be questions now, or
the slides are visible, right?
Yeah.
Okay. So thank you everyone for having me here. My name is I'm Raja Appuswamy. I'm an assistant professor in the data science department at EURECOM. EURECOM is a grande école, we call it in France, in the south of France. So I'm about 20 minutes away from Cannes, where the film festival happens every year. So if any of you find yourself in the French Riviera region, please look me up, and I'd be more than happy to host you at EURECOM and arrange a talk. So this work that I'm going to present today is on storing and reviving databases using synthetic DNA. And this is work that's I'm only one person who's the face of this work, but in reality it's a large collaboration with many members of the European Union flagship FED project called OligoArchive, and members of the Danish National Archive. Okay, so just to set the context, members of this workshop, people who are attending this workshop already know this problem, but I'll just state it for the sake of context and completeness. So recent studies by IDC report that the global data sphere, which is the sum total of all data generated worldwide, is growing rapidly. It's going to reach 175 zettabytes by 2025, and 50% of this data is going to be enterprise data that's going to be stored in relational databases or non-relational databases. So databases in one way or the other, right? So the angle that I am actually coming from, I work a lot on database systems and data management systems. That's my area of research. And I am actually looking from the point of view of enterprise databases, customers who run large-scale databases. And I am actually looking at the problem of explosion of data over the last few years in enterprises. There is recent studies from Horizon, just another reporting agency, which also says that, an analysis agency, which says that nearly 80% of the data is cold, meaning it's infrequently accessed. So a lot of data is being generated, but 80% is cold. And this cold data is increasing at a 60% cumulative annual growth rate. So the cold data is increasing faster than warm data. So this is kind of an interesting twist in the sense that enterprises probably are gathering data for running machine learning models or artificial intelligence or whatever it is. And then once they use the data, they keep the data around. They need to keep it in order to meet regulatory compliance or legal requirements. And this data becomes cold. And they have to store it, and they have to store it for longer and longer time periods, right? So typically, if you look at the enterprise storage stack, I'm showing you on the figure on the left here, the enterprise storage stack is multi-tiered. We use multiple storage devices. And you can see that these storage devices, there is a trade-off between the cost of the storage device on the y-axis and the latency of access on the x-axis. So typically, you store data that you need fast access, typically like real-time analytics or something like this. It's stored in DRAM or SSDs, solid-state disks like flash. Data that you need slower access, you store it on hard disk drives, and data that you really need to archive, you store it on tape. So probably the people here who are all working with archival data and the point of view of preservation, you're probably used to tape a lot more than these high-end high-performance devices, I guess, right? So the right-hand side shows you the typical architecture that databases use today. If you want to archive data, so you take whatever database you have, whether it's old SQL, NoSQL, or new SQL, it doesn't matter. You take a database, you run a tool that will basically dump the data from the database in CSV or SQL or whatever format you want. You take it and you store this dump on your on tape typically. Oops, sorry, I just need to move back there. Yeah, and later, how many years later you want to restore it back, you're going to take the data from tape and you run a tool that basically restores it back into the database. And the problem is that the current mechanism, the current approach we have today of using tape, it suffers from fundamental limitations that's really threatening our ability to store data, especially enterprise ability to store data for a long time. So what are the problems with tape? Here is a survey which if you haven't heard of it, I encourage you guys to take a look at it. It's from the Storage and Networking Industry Association. It's called the 100-Year Archive Survey. And basically the SNIA members went and interviewed a whole lot of people. And I think this includes people from museums and archives and memory institutions about the data requirements they have and how long they store the data. And it turned out that 60% of archival data is stored longer than 20 years. And this is even common enterprises. And if they look at museums and memory institutions, it's no surprise that they have to store the data forever. So there was no really time frame there at all. So it had to be stored longer than 50 years or maybe even 100 years. So given this large amounts of data needs to be stored for very long time periods, this in essence creates the problem. Because on the left, I'm showing you the lifetime of various devices we have today. And you see here clearly that the devices, flash and hard disk drives, typically last for about 5 years, while tape lasts for 10 to 20 years. You could potentially push it to 20 years. But the problem is we need to store data much longer than 20 years. And this is the first problem, the fact that we have media decay. And the second problem is the fact that we have media obsolescence also with tape. Because what I'm showing you on the right-hand side is various versions of tape. So every 3 years, the linear tape organization, linear tape open standard comes out, a new standard comes out, and tape vendors migrate from one generation of tape to the next generation of tape. And typically when you migrate, you get a pretty big improvement in capacity. So there's a good incentive to migrate. But tape vendors only support backwards compatibility up to 2 generations. So if you're using LTO6 tape drive, you will be able to read LTO5 and LTO4 tape cartridges, but not 3, 2, or 1. So that's why I've highlighted it in green and red. And you can imagine as years progress, this is putting a huge amount of stress on enterprise archives or pretty much everybody who's using a tape. There's a very strong motivation and incentive to migrate, because if you don't migrate, you will not be able to read the cartridges using the latest technology anymore, right? So the net result of this has already been written. There's this fantastic article by Marty Perlmutter where he talks about how the Hollywood archivists can't outpace obsolescence, and how studios invested in magnetic tape are really struggling now. And to quote him, he really says that there is going to be a very large dead period from late 90s to 2020 where most media will be lost. And he talks about the Hollywood archives here, and I think we are actually like, we wouldn't be, it wouldn't be too much of a stretch to say that very soon, at the rate at which everybody is gathering data for AI and machine learning, this problem is looming on the horizon, and it's definitely going to hit enterprises at a large scale. That's what I imagine. And this is also the reason why I think the work that this community, digital preservation community, has been pioneering over the last several years, I think it's going to have a much broader impact in enterprise databases also. And that's the angle that I'm actually coming from. So what we are doing is we are trying to basically tackle this problem from the ground up at the root level, going at the media itself. So we believe that magnetic media is only one possibility for storing data. And what we are investigating, what we are looking at, is using DNA as a digital storage media. So what the DNA that I'm talking about is exactly the same DNA we all have in our bodies. It's the same molecule that's been used by pretty much every living organism on Earth for passing hereditary information from one generation to another. So for a quick biology recap, DNA is really, it's a macromolecule that's made up of sub-molecules called nucleotides. So there are 4 types of nucleotides, A, C, G, T, and that's all you need to know for the point of this talk. And a DNA strand, or what we call an oligonucleotide, is a linear sequence of these nucleotides. So when we talk about DNA in terms of data storage, we're talking about single-stranded DNA that's actually manufactured outside the body and stored outside the body. Yes, absolutely nothing living about it. We do not inject this DNA in a cell. We're not going to be manufacturing viral sequences, so there's no need to panic or worry. And the figure here shows you the typical steps involved in storing data on DNA. So what you would do is you start with the binary data that's shown in the middle. You would run an encoding algorithm that converts the binary data into oligonucleotides, strings of ACGTs. Then you would use a biochemical process called synthesis that's used to manufacture actual DNA. This is the same synthesis process that's also used to manufacture DNA vaccines or RNA vaccines that are used for COVID, for instance. Then once you have your DNA, to read the data back, you apply sequencing technology. This is the same technology that's used to read your genome, for example, in order to diagnose a specific variant of cancer or to identify if you have some mutation that's deleterious. So you use the same sequencing technology to read the DNA, and you decode the data back to convert from ACGTs back into binary. So this is the cycle involved in using DNA as a digital storage medium. Of course, before I tell you the challenges involved in this, it sounds pretty simple and straightforward. But before I tell you the challenges, we have to ask the question, why DNA, right? There are 3 main reasons. The first reason is shown in the graph on the left. This graph shows you the potential that DNA has in terms of storage density, and it shows you compares the density of DNA with future projections of storage density of various devices. And as you can see, tape obviously has the highest projection, and DNA is about 6 to 7 orders of magnitude denser than tape, because it's a very, very dense 3-dimensional storage medium. So this is the first reason why we want to use DNA. The second reason is that DNA is very durable. There is this recent experiment from Professor George Church at Harvard, where his group actually went to Siberia, and they dug up the permafrost fossils of an animal species called woolly mammoth. The last species lived about 4,000 years ago. They extracted the DNA from woolly mammoth, and recently they have established a company now to de-extinctify or to make woolly mammoth, to bring it back to life. So they're going to use the DNA extracted, use it with gene editing technology to see if they can actually modify the gene of an elephant or one of these other species we have to bring back the woolly mammoth to life, right? So they have recently established a company on this. Fascinating topic. You can go and look it up. But this really shows you that DNA can survive for thousands of years in reasonable environments. And the third reason is that as long as we have the need to see, as long as we have we live on Earth, we will always have the need to sequence DNA, and this is growing more and more, and we'll always have the ability to do it, which means that the technology to read DNA is always going to be there. So it has kind of an eternal relevance in that aspect. So given these aspects, we have established Project OligoArchive, which is a EU-funded future and emerging technologies project that focuses on using DNA as an intelligent storage medium. And we're attacking multiple layers of the stack. So we really want to build essentially a DNA disk that can automate synthesis and sequencing for writing and reading DNA. In fact, you can translate some operations, some SQL operations, into biochemical reactions that directly run on DNA, and we call this near molecule query processing. It's fairly more complicated, so I won't talk about that in this talk, but it is one part of the project. And we are also implementing operating system abstractions. Like, for example, you don't want to deal with DNA, you don't want to deal with biochemistry, you want to read and write files and directories. So how do you implement a file system over DNA? And similarly, how do you deal with various problems involving storage of data on DNA? So the Origo archive focuses on that. So here is the rough architecture of how we envision DNA will be used and how we envision DNA storage will be used. So essentially, on the right, I show you a DNA storage, which is as a black box. On the left is your DBMS. What we will have is an archive utility and a restore utility that's going to convert binary data into DNA strings and basically take DNA strings back and convert it into binary data. It's a very, very simple representation, that architecture that we envision. And you can see here that we are abstracting out DNA, right? So we are treating it as a black box. Now I would like to, so the rest of the talk, just peel off one of the layers and show you some of the complications involved in using DNA as a digital storage media. So I told you that in order to store data on DNA, you need to encode the data binary bits into DNA strands, right? It turns out that today, because of synthesis limitations, our capability to generate DNA is limited to a few hundred nucleotides, which means any data you store is going to be spread out across millions of DNA strands. But DNA itself has no addressing. So you need to add additional information in the DNA strand during encoding to order these DNA strands. Okay? And once you synthesize the DNA, the chemical process that manufactures the DNA, and you sequence the DNA, what you get back is corresponding copies of the original DNA strand. So I'm showing you here. And synthesis and sequencing are noisy steps. So there is a lot of errors in this process. And so you need to apply a consensus procedure to be able to infer what data you actually store before you can actually decode the data back. So there are many, many issues here in storing data on DNA. And what we have done is we have basically built a system that actually solves most of these problems, or solves all of these problems. And in order to demonstrate that the system works, we are collaborating with the Danish National Archive in preserving and in storing some culturally significant artifact digital data on DNA. In this example, in this project especially, we are actually storing the hand drawings of King Christian, which is a very important culturally significant digital data that Danish National Archive has. So we took the drawing, the Danish National Archives gave us a CR'd archive of the drawing together with a whole lot of metadata about the drawings. And what I'm showing you here is a very high-level overview of a sequence of steps that we apply to this CR'd archive to convert from the binary into the DNA strings. You don't have to know about the details, and it's probably not of interest to this community, but we apply techniques from error control coding in order to protect the data from errors. We add addressing information in order to reorder the oligos, and we apply various aspects of constraint coding theory in order to be able to deal with the errors. And we also developed a new consensus algorithm that can infer the data, the original DNA strands that we stored from these noisy copies. So net, what I want to show you here is we have a full pipeline that's actually working, that's functional, that can convert binary data into DNA. And it turns out this project will be, we are in the process of doing our wet lab experiments and completing this project, and it will be the third largest DNA storage experiment ever done. So we are converting 12.5 megabytes of data into nearly 500,000 DNA strands. Now, before just one last minute before I conclude. Oops, sorry, I think I switched. Yes. So having shown all the promise of DNA, sorry, I keep switching back and forth. Having shown the promise of DNA, I want to say that there are definitely open problems. So I'm going to play the devil's advocate in this last minute. DNA synthesis today is about 10 million times more expensive than tape. So we are pursuing novel research in the project and outside the project on novel synthesis techniques for bringing the cost down. So this is not going to happen in the next year for sure. So it's more of a 5 to 10 year horizon that you're looking at. The second thing is that the automation performance of synthesis and sequencing needs to improve. So today we are looking at a throughput of around kilobits per second for writing and megabits per second for reading. So we need to knock that up by an order of 10 or 100 in order to solve this problem. And this is also being worked on. And finally, DNA does not solve the media or format obsolescence problem. So while CR'd format helps with format obsolescence, I think there is still an open question about what happens with non-standard formats, especially in the industry, where a lot of data is stored in data lakes in non-standard formats. So there's an open question about that. And finally, there is also the question of who preserves this whole decoding algorithms used for recovering data from DNA. And there we have a collaboration with a company here called Upalia, which works on emulation. So we're combining emulation with DNA storage. So to conclude, we think the contemporary media suffers from limited lifetime and suffers from media decay and obsolescence issues. DNA provides a biological alternative, but definitely does not all solve problems. And I think there are many areas of collaboration here between OligoArchive and members of the digital preservation community. So please feel free to reach out for more collaboration on this topic. Thank you.
Okay. So hello and welcome to my presentation about database preparation for industrial customers. My name is Florian Hartl, and for the last 7 years, I was working as a specialist for application retirement and producing and archiving data for the industrial customer, mainly for the automotive industry. At the beginning, there was planned that a colleague of mine will join the meeting or join the speech, but he had some termine issues, so he's not here, so I will do it by my own. So then what is my company doing? My company is CSP. We are working in the near Munich, and we have 4 types of software, and 3 types of our software is for producing data. They're producing data at the automotive industry, chemical industry, or other industries. And the last software from our side is called Chronos, and this software is for storing this data and archiving this data for the next years. So, for example, our customers are companies like BMW, Porsche, Mercedes, Bugatti. Every big German car manufacturer is a customer on our side, and every time you go into a car from a German brand, there is some software from our side that they used to produce the car. And what is the data we are working with? So I think all of you knew what a screwdriver is and have used something like this to put up something from IKEA, for example. But I don't think you see something like this if you think about some screwdriver. So these are things to produce a car. They are heavily expensive. This is about 5,000 to 10,000 euros. And these are
sorry, Florian. It looks like you're showing something.
Yeah. Oh, don't show it?
Yeah. Oh, yeah. Sorry. Now I can see it.
Okay, so
I hope everybody else can see Florian as well.
So these are the screwdrivers we use for our software, and they are heavily expensive, as I said. They are around 5,000 to 10,000 euro, and they, for example, only work when they are used in the right position. So at the moment, I even cannot use it because says this is nowhere it should work, because this little thing says you're not allowed to use this screwdriver at the moment because you could hurt someone. And these things produce a lot of data. And our event here is for preparing data for the next 60 years to 2080. And for the automotive industry, the time span is not so long. With my customers, most of the time I talk about the next 30 years. Why the next 30 years? Because there are some compliance officers in the company that says 25 years they have to store the data, and 5 years of buffer we need to store the data for this car. And why this is 30 years? In Germany, we have some cars that called old-timer. They are 30 years old. When a car runs in Germany for 30 years, then this car is an old-timer. And at this time, this car is managed differently, and it's a special car. But before, these are the normal cars and the most people drive. And for this time, we have to store the data from the screwdrivers and from everything else. So it's not only the screwdrivers, maybe there's everything they need and they are using to produce the car produces data, and this data is stored in our systems. And what they want with this data. The fun fact to this, they don't even know what they want to do with this data, but they are storing it because there could come some legal actions in the next 30 years about the cars or about one car that they have to think about, and that they have to guarantee this car is produced correctly the last 30 years. Or this car is, for example, 20 years old, and 20 years before, this car is put together as it was sold 20 years ago, and it has to be, they have to guarantee it, because maybe there was some error in the machine here, for example, so this could make some damage to the car, and the brakes did not work, and there was an accident. This is a really big problem if there is something like this, but hopefully most of the time this will never happen. Most of the time, if something happens like this, it happens in the first 3 to 5 years or never, but they are storing the data for 30 years. And what is important for them if they store the data? There are 4 things important for them. The first thing is a safe storage. Safe storage means they store the data on multiple infrastructure. And it's not only stored at one point, it's stored all over the world, for example. Then there's revision security that goes on with the safe storage. This means this revision security, these are storage systems that are not allowed to change. It's called warm system, write once, read many. It just means there's no feature to changing or deleting the files. And this is very important because they have to guarantee, if they give the data to the government, for example, or to a lawyer, they have to guarantee that they have not changed the data. I think you all know the Faria scandal of the last years. This was an example for this. Faria was not customer from CSP before that, and now they are. Because of that, they were not able to guarantee this. Okay, you have problems to see me? Okay. And so this is very important for them. They have to make sure that there's no change to the data. Okay, and then there are 2 more things, and this is documentation and knowledge. What you need for this data they are archiving. Because they don't know what they want, they have to put the entire knowledge into documentation of the data. Because when they are doing the archiving, they put everything together, they make their thoughts about it, they say, okay, what do we need, when do we need it, how do we need it? And then they put it into the archive. And then there will, in 20 years in the future, someone else has to analyze this data. And if without this knowledge in the documentation, there's close to no chance to get deep into the data, or you have to work for multiple weeks to get what the data can deliver to you, what's in the data, and if everything is right. I have done something like this before. I'm not so old, I'm 27 years now, but I have worked with data from the 1970s. I have worked with old COBOL programs. They were so old, there was not even a possibility to read them with normal computers. We had to change the encoding of the files we get from them, and they had no idea what is in these files. But they knew they have to, in the data they need at the moment, because there was a lawyer at the door that asking for this data. They didn't know what type of data was there. But I had to analyze it, and this data was produced 20 years before I even was born. And this was a hard task for me to do, because nobody could even tell me anything about this data. I had to read multiple tables, multiple databases, some very old code lines to get what they wanted to do back then. And this is really how important the knowledge is for the archiving data for the industrial companies, for the automotive industry. And because without it, they can have petabyte of data and not even use it. For example, this is at the moment, this is the standard they are using, and for the last 15 years, with these screwdrivers all around the world, it's about 15 terabyte they are produced in 15 years. In the next 5 years, this will change completely. In the next 5 years, there is some increasement of this data, and after this 5 years, we expect the data be the same amount we had in 15 years in 1 year or less. They will just completely change the way they get the data. This thing can just give a small amount of data to the customer or to the system. But the new type of screw drives will expand that. They can give everything to the system, like the temperature, the water in the air, the water on the floor, everything. They just imagine a screwdriver then can get if it's a woman or a man is producing a car, because this could be important if it's a guy with 2 meters or a small woman with 160. This can be important, and they will save this for the next 30 years. And this is why the amount of archive will increase drastically in the next 5 to 10 years. And when you're doing this archiving, we are always doing this in 4 steps. The first step is the step about the knowledge. And this step takes a very long time. We really get together with the people at the factory, with the people of the IT, and talk to them. What do you need? Because the people that are producing this data are not the same that will store this data or will work with this data in the future. The people who are producing are just workers. They produce data and say, okay, store it. I don't know why I want to use it, because they will never have to use this data they are producing. The IT will have to read the data others produced and have no knowledge about the processes of the production. So the identifying process of this data is huge. So we have to talk to multiple people in the factories, in the IT sector, and to say, okay, what do you need? How do you need it? How long do you need it? And what do you really want from this data? You need any reports. And then you put this together and say, okay, I have everything I need. Now I can do the archive. And the archiving point is just the raw work. It's not a big deal. If you have done a good identification phase, the archiving is just, okay, I click my button and it will run for a few days, for example. And after this, everything is fine. Okay. And then if you have done the archiving, then there are 2 more phases. The first of these 2 are the reusement phase. So this means you have put the data to the archive. So you will not need it anymore in your system, because in the systems, the system will grow bigger and bigger and bigger. And no database, for example, could even handle that. So put this data away, but not delete it. It just means this data is in the archive, and the newest data always is in the database, the old data is in the archive. And after the 30 years, you can go to the last step, and the system will do that for you, probably delete this data forever, because then it's when it's not needed anymore. And how do this looks like, or what you can do with this, or what is a technical way to do it? You have multiple sources where this data can come from. You put all these sources together in a system, in an archiving system. From our company, it's called Kronos. There are some others. This puts the data together and then splits it up in the raw data and the metadata. That means you get something like CSV files to store the data in the future, and something like an XML file with the meta information about the database, about the data source. That means you have just readable text files to store the data. I'm not a friend of encryption or something for data, for archive data, because it's not so easy to read the data without encryption, and you don't know in 20 years is an encryption like this we have at the moment, or did it change completely? Is Java even working, for example, in the future? Maybe you cannot even decode the files. So just put simple text files. We have no CSP format for these files to use, because we cannot even say if there a CSP in 20 years. So that's why we are using really standard text files to store this data. And these text files have some hash values. With these hash values, we try and we are able to check if this file changes. When there's some storage system, they can do it too, but we can change, or we can check the changes every time. My colleague that's not here today, they have a system that can check this on the fly. So if you type in on a system and change a file, that this system will automatically, when you try to save it, will say, oh, you tried to save a file that's not allowed to save, and will automatically create a report and says, okay, no changing anymore. Because this is so important that you can guarantee you have unchanged files and unchanged data for the future. Because if there's changes, you will ever have a problem with the lawyer or the government. These problems could be so huge, it's better to do some good preparation and everything is put together. So
it works.
Works fine.
Okay. Hello again. My name is Klaus Rechert. I'm here at the University of Freiburg. We are doing emulation for quite some time. I personally started with emulation 2009 during the Planets project, and the topic stuck with me. So my talk today is about to put a bit of a different perspective on this, mostly challenged by your very nice challenge you presented to us in last April. Is it possible to access today's databases in 60 years? And this is a mind-provoking, but I think mostly a theoretical question. Mostly because databases is a weakly defined term, at least from a computer scientist's perspective. There are many different types. You can have the data in many different types. So there are a lot of questions here. And of course, databases are not a standalone product typically, but they are embedded somehow in a wider context, either business or administrative processes. So my questions I want to tackle a bit is, can we plan actually for 60 years? And what is the resulting risk profile? So if we take a look in choosing a strategy, so we have already heard one or two data-driven strategies. So this is where you could look at the data. So you extract the data, do a SQL dump or similar, you migrate to this data or keep it that way. You generalize the data to CSV, CR, or similar. And then you have to push something into the future because someone in 30 years, and 60 years, has to reconstruct this data meaningful. And this also requires to rewrite queries, replace and substitute clients, especially if this was embedded in a larger process. The other approach I'm focusing this talk is a software-driven approach. So we focus on the software, describe and manage a technical stack, which it boils down to an emulation strategy, and provide interfaces which enable you to access these databases through native interfaces, whatever that is. For that databases, could be a UI, it could be a ODBC over TCP/IP, it could be an original software client, etc. So there is a lot. Of course, there's a lot of middle ground in between, but I'll leave that for the discussion. So if we take a look at a software-based approach, well, you can follow up a very lazy strategy. So it's all about complexity. If you have a do you have a commonly widely used database software like, I don't know, a MySQL, Maier, DB, Postgres or something, open source, ideally, a simple setup where just a default setup where you just have some tables with little manual customization required, and especially limited interaction with external system, well, and if you're able to bear some risks, well, you can outsource the software preservation part. The Software Heritage Foundation, for instance, preserves source code. So you will find in the future the source code of MariaDB or Postgres, or I don't know, even NoSQL databases. You create some metadata. It can be even informal. Well, this database was used with this version, whatever. And well, take it for your ride. That's very simple, but it also quite risky. No one actually ensures you that you actually capture all the software well. No one actually ensures you that you are able to reconstruct it based on anecdotal metadata or even formal metadata, but you never tried it. So if you want to mitigate the risk, well, you have to use something like a contemporary emulation framework and create an installation of the database and deploy the data and to just verify the result. This is the only actual way that you make sure that it actually will work in the future. So let's take a look at the technical stack. So we have it's a standard computer science technique. If something is quite complex, you divide it into layers. So on the top layer, you have the data, which I assume you already have precautions like put it on tape or even in a DNA store. You have the database software, which is running in a configured environment, which is a Windows or Linux or some other operating system with some additional software installed. You have virtual hardware, which relates to an emulator, which is then rooted on a contemporary CPU, which manages connectors to machines and users. The good part is a manually installed software stack will result also in a good documentation and in a detailed documentation, which is very important for verification. So if you have that, we are starting again with complexity. So if you have only a low complexity, so for instance, SharePoint is a very good example. You have a SharePoint backup, you know the version of the SharePoint, we can create very simple installations which act as templates, and we can use these templates where we ask a user only a few questions, like the name and IP addresses, maybe a default user, and just reinstall this on top of a standardized common SharePoint installation. This scales very well if you are able to reuse these stacks. And this is actually something where you can observe the first very important lever of an emulation strategy to make it scale. You have to cooperate. The other important mechanic for emulation to scale is to automate, to make it very simple. Once you have it, it's not that hard to install and maintain such a stack, for instance, or MariaDB installation, and it's not that hard for some people in the community to create scripts that allows you to automate that installation. So in this case, you focus just on the data and use a template because your installation is pretty simple. The main advantage is you can keep the data separated from the images, and you can just rely on these template images, which are maintained by the community. If your database stack is more complex, you may want to keep both things together, and you may need also a customized installation procedure. Also here, the main lever for making things scalable is reuse common parts. So don't start from scratch, but start with an emulation framework which already has pre-installed Linux or Windows systems. There are also plenty of automation options here. It's most importantly that you implement automation when you do installation, because this is also a very good source for future knowledge extraction on operating such software systems. And of course, again, cooperate, share these examples and share the base images. If you have a very complex system where it's very difficult to extract the data and the configuration, you have to resort to a full system preservation. So this is in typical situation, or if you're lazy, this is you export or import such a system from the cloud, or you take it from a real machine. In both cases, you have to think about hardware dependencies, both the client machine, even though it's a virtual machine, and especially hardware machines are tied to real hardware and have expectations how hardware work. This is automatable, but also requires some knowledge and can be shared with the community. The other option is to rebuild the machine from a file system or a backup, especially if you have a full file system backup on tape. There's a very convenient option that to bring that together with a container and make a full system image out of it. Again here, reuse common parts, especially the knowledge on generalizing hardware. There are plenty of automation options here, so we can spare that for the discussion and cooperate with the community. So what have we learned until now? So there are different options to preserve a software stack and to rebuild it. And if you observed it well, we excluded the emulator because the emulator is software-based. And this is something that will not sustain 30 years or 60 years. So if you follow up emulation-based strategy for preserving something like software or a database, you have to prepare for obsolescence. But there is a good thing about it. Everyone has exactly the same problem. It doesn't matter if someone is preserving SAP or if it's an Oracle database, or if it's something that has been executed or runnable on an Intel computer. So from today's perspective, I think it is a safe bet that we will see other Intel-based emulators in the future. So what your preparation task is to prepare the images, and that's what I mean with hardware, generalize the hardware dependencies, to migrate them on new virtual hardware, because this is a task which we will face for sure. The other important observation is complexity matters. The complexity of your installation and the risk profile you want or you're able to accept should guide your options, which route you take. Do you take a full system preservation or you take a template-based approach? And the other good part is, I noted it a few times, but I think I have to stress it a lot, is scaling emulation. Emulation scales well with users. The more users you have, the more people are in the same boat. So there are plenty, so yeah, please cooperate. I can talk about the easy project in the after session. And there are plenty of automation options. I have to hurry up because I want to show you something more forward-looking. Until now, we have discussed emulation as a conceptual strategy, or conceptual approach. But emulation is also useful for as an access technology. So first, we need to contextualize the software stack. So we have to build interfaces, interactions between software stacks, and we should be able, we need to be able to also rebuild, as we did with the software stack, also administrative or business processes. Otherwise, we do not know if we have missed something. And the other options I want to promote here for when you think about emulation. Emulation is a tool which enables you to prolong the sunset phase of obsolete services. We call that continuous access. So contextualizing the software stack. So in this case, you see a very simple example where we have two stacks. We have a database running in that software stack on an individual machine, and you have a front end, a client, which is, I don't know, software or a browser. And we need to bring these two together. So we have to extend the scope of emulation by enabling to describe and to interact instances. We chose to emulate copper, which is cables and mostly Ethernet components, because they are very simple to re-implement. Ethernet packets are simple to understand, and every other higher protocol is supported. The other problem we solved, or we tried to solve with this approach, is security. If you prolong the lifetime of an obsolete system, you will face security issues. The service I will introduce today is fully isolated and contains integrated network service like DHCP, DNS, etc. But also it can Active Directory, LDAP, or other IDP services. So it's fully independent, and you can rebuild the old system as it was. And the other part is, even if you want to have a full isolated system, you still want to integrate it into current services. So we have to build something to integrate network services into current workflows. So how does it work? Once you have the software stacks, you just build a network. So you give it a name, you give it a network range, you choose a few options, what services you want to make available in this network, and then you add machines to it. And every machine can have a full qualified domain name. That can be a simple server name, but it could be any domain name, because this is an isolated network. So even Landesarchiv.de or Microsoft.com will work. You can give it an internal IP address. This is important if your service relies on the IP, and you can forward external ports. In this case, it's the 1433, which is the SQL port. And this is the result. You see, you can fire up the machine. You can switch. This is a very simple network which just has the DHCP service and the SQL server running, and you can use it interactively. This is the old, more or less the old style of emulation. So you can put more and more computers in there and switch between these machines. But I want to show you something more than that today. You also can connect from outside. So we implemented a very simple user space application translating these Ethernet packets into a TCP stream, which is then available on your local machine or localhost. This service can be started automated from a command line if you want it, or from the web, as I will show in a second. And it is able also to start up the emulated network session. So if you request to connect to a database, it will start the whole network immediately with the request, and this will take about 30 seconds. It depends on your computing network, and then you're able to connect. And this is also the point where we can integrate even more emulation options, because we can do protocol translation here. So I have 2 minutes left, which is I think just enough to show you this very simple example. So we run it, and I can show this example during discussion. So we can also, I only have one slide left, my summary. So I can show that afterwards, and we can also start discussion. Well,
we're really keen to see your demo. You'll take all your time.
Okay.
But we'll look that Damir is not left behind. I will give you signals.
So you can switch between the machines here. You can see here, this is the DHCP service, and the DNS service is doing stuff. It's connected. So we can switch back here. So the machine is there. I can log in if I want, but I don't want to in this case. So I can, but I want to connect to it. So this will create a local link for me, and this will fire up a proxy, the proxy application, which is automated by the browser. And you can see this is the nerdish view of it, that you actually can see that it actually works. So you see the proxy got connected to the network, so it has been attached to the hub and requested a DHCP address, so it got a DHCP an address in that network. And now I can do something with it. This is my Excel. It's the genuine Windows Microsoft one, and I can. So it's in German, but I think you get the idea. I set up a DSN yesterday, so it still had some default settings. So if you see, it has nothing in it. It's just the port, and it's just this driver, and I connect to it. So I have to do the authentication. Sorry, I mistyped it.
As a non-technical person, you're trying to access a SQL server that runs on your stabilized platform, which is fairly open via access, right?
Yes,
via Excel.
This is there's the Northwind example running on which I installed via template into standard SQL 2000 version 8 database running in the cloud. I connected to it. This is a secure connect. It goes directly to my localhost port. It's going. It is authenticated via OAuth 2. It's HTTP based, so we do WebSockets. We do Ethernet over WebSockets to the cloud machine, and this is connected. So you can see here. That's the name of the machine you saw, and this had also an IP, and it tries to do some Windows ports, but that we don't care about that. I can select now something. I can think this is the way how to do it, and now I can see the data from the archive. I could use other tools to do an ODC-PC interaction with the database, whatever. I can also use RDP to connect to the machine instead of the web browser. I can do SSH. I could automate this to connect this into my system as needed. A very simple example where you see this fully installed is this is a website, a web project. It's a wiki-based project with which is running. It's online again. It's running in a full emulated service securely, so you get a private connection to this. Also on the web. So let me conclude. Well, there are more options to this. RDP said we have a Flash-enabled browser, so ask me if you want to see more. Just to conclude. Emulation is a software-focused strategy, so the implementation depends very much on the complexity and the anticipated risk profile. It relies on the future, on the availability of an hardware emulator in the future, which is pretty good for Intel. It might be less good for Spark or PPC. It scales with the availability of pre-configured stacks, so there are plenty of options for cooperation and automation. So if you cooperate and automate, it will be very easy to use it. Emulation is also a tool to prolong the sunset phase of obsolete services, which I showed. So you can still use the databases, you can still give access to certain groups of, and you can adapt the front end to this over time. So you can re-implement just the front end if needed. And this service I showed you, this case very well with the number of called instances, because you only use CPUs and for instances which are actually in request. Most of the instances are stale because they only get requests, I don't know, 20 times a year. The downside that's under development here, so this is our current research focus, is operating system, obsolete software systems remains a huge non-technical problem, but there are some technical solutions possible. I'm also happy to discuss this further in the discussion. So thank you very much. I'm happy to answer the questions.
I think it's best if we have this lively discussion. I will show what my software does, not at all as something to persuade you that you should use it, but to give you a context of my experience and experience working with different databases. So I'm the CEO of Spectral Core, and what we make is database-related software and mostly database migration software. And if you want to ask us in one sentence what to do, is we copy data from different databases from one to another. If they're same type, different type, same version, different version, we simply make this a non-problem. Now my mouse is gone, but okay, just a moment. Computer is acting up, of course. All right, so we support something like 40-ish databases. We got rid of some databases have obsolete drivers. We also support big data migration to the cloud, and so columnar data. In short, we have a lot of experience with all kinds of, from ancient file-based databases, we wrote our own database drivers to the latest cloud things. Okay, so this is software called Full Convert, and why is it important? Because it fully supports CERD. It gives you the, as I said, we support something like 40 databases, and CERD we treat as a database, not as an archival format. So we take care to transform data in memory and optimally write it to CERD, which gives you the ability to read from 40-ish source databases and create CERD archives with just a few clicks. And it works out of the box with no customization needed. It also gives you the ability to read CERD archives and extract them into existing databases. I'll skip a bit further, just so we have more time for discussion, because I would like us to, I would like to my views to be challenged, because we all learn more of this. So Full Convert is like the software that people use for extremely easy migration of, let's say, data in the local networks. But when they're going into cloud from database on premises or from another databases on the cloud, we need more firepower. So OmniLoader is our enterprise class product. And what you see here on the top, those are all computers. So we have, I think, in this instance, we have something like 18 agents running on 18 machines, copying databases with hundreds of connections in parallel, slicing tables automatically, loading data in Parquet format, transforming partitions to other types of partitions, and all of this is done in parallel and sequentially, depending on what's the most optimal way. This works on Windows and Linux, and so the database sizes that we have here is typical in the range of 10 terabytes. 50 terabytes is something that we should be doing soon, and we have client mentioning that another client will have a 100 terabyte database, 100 terabytes in size, which is important because we are going to be doing mentioning CERD later. This tool is called SQL Trend, and its code is for the translation. It uses translation of stored procedures. That's also something that I didn't hear mentioned here, but it's stored procedures are not strictly data, and I think we should be liberating data from the database format. So I'll take the opposing approach compared to Klaus. I think we have to extract data from the storage container or the system it's in, and copy it somewhere where you have the full control, because that's the only way to preserve it for a longer time. Even now, it's hard to work with existing databases. It's even harder to work if they're old. And my view is, yeah, I also agree we should prepare for obsolescence. But the way to do this is to make something that works great today and for the, let's say, next 5 to 10 years. In 10 years' time, we'll make another layer over that to take new reality into account, right? Okay, we also built a database documentation tool. It's now pulled from a website because it's going to be merged into another product, our upcoming database manager for the cloud and on-premises databases. And now let's me go. As mentioned, I think software for working with CRD is extremely good for working with CRD. On the other hand, I would like to propose to share with you my view that CRD is a format that's not good for the future. It's useful now. It shows its limitations even now. And in the next 5 years, it's not going to be very useful at all. Because databases are getting larger and larger, databases are getting wider and wider. We are having everything in clusters. So the way we support CRD is, you know, read whatever you have, we'll make CRD out of that. As we treat it with the database, all the full customization of our software is used. So if you need to transform data moving into archive, and we wrote the highest possible writer we could. Now we come to the inherent limitations of CRD. And the inherent limitations of CRD is we have something that's not really designed to be an archive. It's a single file, and that single file is hierarchical text format. It's super verbose, and so we zip it and make an archive out of that, make a zip file. But that's a crutch, so that's not fixing the issue. We get to the point where we have more data as a scaffold for the original data than we have data in a CRD file. So, for example, this full convert software that's super easy, that makes it super easy to extract things into CRD. In its most powerful plan, we have 16 parallel connections, so we can process 16 tables at the same time. For example, when you load data into Postgres, we get millions of records per second. But for CRD, there's not so much we can do, right? Because building XML file and zipping it has to be streamed. This stream means it has to be done by a single core. It's a single process, even single thread, right? In the multi-threaded process. So we can prepare, 100 gigabytes of data extremely quickly. And then we're going to wait and wait and wait until we build that XML fully and zip it. So there is, again, we have several other helpers, but I would still say those are crutches, because if you try and save large blob means binary large object like an image, presentation, or even a video. You can do that in the powerful database. I try to fix that into XML. You get this C data section. You have to encode it in base 64 format. It's inefficiency on top of other inefficiency. So you cannot even save it in a single file, because if your video is large, you can say, okay, but files can be large. Well, not really, depending on the file format, on the operating system. Files can be like, it can stop working when you get to a few terabytes. You can have a file that after a few terabytes, you can no longer save it. So CRD is good for small datasets now, but even we cannot work today with data that we work with for our large enterprise clients. So we even didn't try to support CRD nomni loaders because there's no point. This is for big data. And here's now I'd like to give you a context for the I'd say the direction I believe that we should be heading in. As you probably saw, processors aren't really getting faster. Back when I was young, a long time ago, every time I bought a new computer, it was 3 times faster. Today, if I buy a new computer, the best computer the money can buy, it will be exactly 10 to 20% faster. And we have more cores in the CPUs. Each of those cores can actually get slower than before. So for example, if you have 16 core CPU, you can process 16 things at a time, but each individual things might even take longer than the last generation. And when we go where things are going, everything is sliced to be horizontally scalable, which means if you are encoding videos, you will split it by frames and you will encode it on 500 machines. It will cost you roughly the same if you encode something for 500 hours on a single machine or 1 hour on 500 machines. And so it's looking at how the world is changing. Single file is not going to cut it, and it's not even cutting it today. Florian mentioned the data, only the data from the screwdriver is now, I think, 15 terabytes. And we can expect a 10 times increase in the data volume. So everything now produces data. We can expect the exponential data size to continue. So with any file, single file based format is going to basically be unuseful in a very, very recent time. So I described in an email I sent to a mailing list the format I propose, and it's like high level overview designed really, to provoke discussion. But just in short, I'm going to mention that we cannot really use one format to both encode complex hierarchical related schema and the data. And the data can be in all kinds of different internal formats. It can be row-based data like Excel documents. It can be columnar data. It can be hierarchical data. It can be object data, and so on and so forth. So what we use in OmniLoader, for example, in OmniLoader, which is our tool to migrate data from local on-premises, database on-premises to the cloud. We read data, we transform it into an extremely highly compressed columnar format. We encrypt it, push it over the network, and there we decrypt it and push it, ingest into the target in a highly efficient way. Columnar data is 10 times better compressed than row-based data because we're basically compressing similar things all the time. And of course, you need to have chunks because otherwise you need to read the whole table. This potential form, I believe that basically the ideal format for archiving is very similar to Parquet. Our format internal use is also similar to Parquet, just uses the much stronger compression. Basically, if I would go and invent a perfect archival format for today's time, it would allow extremely quick searches. It would be columnar, and it would not be in a single file. So when we go into the data, we really need to be able to read millions of files that do not have to be on the same machine. We have no idea, even now, we have no idea where Amazon or Azure stores data. In 10 years' times, all of this will change. Few more times. In any case, we need to support all of the data types of all of the important databases and allow the format to be extensible so that one institution can have data types that are really not readable, but some other institution, and when that some other institution tries to read that, they may not have the reader for it, and it's fine because it's not designed for them to have it. Schema, in my opinion, will not really be ever extremely large, but I might be wrong. Maybe later we'll have clusters and thousands of databases be read at the same time. If so, anyway, I propose that schema is encoded in relational tables in SQLite, because SQLite is the most tested database in the world. It's super ubiquitous. It's used everywhere. Browser storage use SQLite. All mobile phones use SQLite for storage. Airplanes fly on SQLite, and so on and so forth. So in short, my idea is, several of my ideas here is, first, liberate the data from the confines of the database system that is built in. So I would use exactly the opposite of what Klaus had recommended. Use different formats for schema and for data, because it's they're of optimal low-level format used for schema is very different than the optimal optimal storage system used for the data. So in C-ARK, for example, each value can be a different file. I propose the data chunks can be anywhere, and our formats can just have a URL reference to it. So it can be on the local disk, it can be on local network, it can be on internet, it can be in whatever system that we invent in the future, and we still don't have now, because nobody can see 10 years into the future. So 8 years in the future is a bit too far, but if you go in increments of 10-ish years, we can preserve the data, and we can, at least transform it every 10 years if possible to some new format that's more useful for that time that we have no idea how it will look like. Okay, discussion time. I hope I'm not over my time allocation.
I'm the Research Innovation Director of KEEP Solutions, and also a computer engineer. And I've been working in developing software for digital preservation for the past 16 years, and specifically also in database preservation for the past 8 years. And I have here to share with you some of our experience and the tools that we developed to support the preservation of databases through the standardization. So this set of slides normally go kind of default for when presenting database, because normally you need to set first what we define here as the database and why it is important. So when we talk about preserving, or when my view on preserving databases is these databases it is the information that is supporting the institution and businesses, which is many times centralized in databases. And we know for a fact in many cases, this information is of great value, and it's preserved for decades due to strategic and also to legal reasons. And these systems are usually complex, as we've seen throughout this workshop, are composed of many software components besides the database management system, and each play their part on the business logic supporting and the submission and presentation interfaces. And in the end, we see that your information ends up being organized in a structure that is specifically optimized for the database and for the original business objectives, which might not yet be the case decades from when it was created. And normally the information that is within the database is not ready to be directly consumed by users, and the user needs might change in time. So the use that you will have from the database might be different. So on our view, there are a few things we try to identify on a database, on a relational database to be specific, that we try to preserve. There is, of course, the content in the tables, which sometimes is enough, is what you actually want to preserve. But many times, to understand this content, you may need also to understand information about the column data types, the relations and the constraints in the table, and you might need information from the projections or views which filter, rearrange, and join the information of several tables to understand it, or actually to filter the information you want to archive. And there's also the behavior or code that might be encoded. And there is other information like user permissions and so on, which might give you a bit of context on how the information was submitted. And in some cases, this might be important. And there might also be information in the system we want to preserve that is not in the relational database, like external resources, for example, files in the file system that are related to the information of the database by application logic. And there are, of course, the submission forms and presentation interfaces that might provide important clues to understand the information of the database, and while the system was being used, of course, and when the information was being submitted. So maybe to recap a bit of everything that we've seen today, there are several approaches to preserve this. Generally 4. The hardware and software museums, which is mainly to do nothing, so to just maintain the system as they are. The emulation, as we've seen, and the one that I'm going to focus more is going to be the file format migration to CR specifically, and also talk a bit about encapsulation. So every strategy, in my view, has advantages and disadvantages. For example, the hardware museums as an advantage, of course, the reproduction accuracy, because it is faithful to the original, because it is the original, right? But of course, the disadvantage is it's very difficult to maintain in several cases. There are restrictions on the access to information. There are, of course, legal restrictions here also into play, and also users need to understand how to operate these long-gone systems and need to operate them in the way they were originally designed, and this might limit the reuse. And in our view, emulation is kind of a similar approach, where you actually just replace some of the parts of the hardware or even the operating system with emulators or other kind of software. And again, the disadvantages are the reproduction of the accuracy, while not having to maintain the hardware or some of the components, but still it's difficult to maintain and to set up, although there might be some the community might help you on this. And again, to use, you need to understand how to operate these systems. So in many of the cases that we've seen, the most appropriate or adequate approach is file format migration, specifically when we convert into what we call a format more suited or better suited for long-term preservation. It's easier to use and reuse, and doesn't have this maintenance of the hardware and software. But of course, the disadvantages are possible data loss during conversion, which you might try to mitigate with quality assurance, and the possibility of having to migrate again with the future, which you might try to mitigate by selecting a format that may keep up with the future more easily. And just to one of the strategies that you might use every time is, of course, encapsulation, which is mainly collection and enriching documentation. With this approach, you might be able to postpone some actions, but it may hinder timely access to information. So we here are the use cases I'm going to present are more in the cases where you actually want to continuously allow access to the content, although maybe with different use cases and different frequency than originally. And it's difficult to gather documentation of complex or closed file systems, or even impossible due to legal concerns, and the quality and completeness of this documentation is difficult without hindsight. So in our opinion, in the strategy that you select, the main problem is that every vendor has its own data types and export formats. And it's rare for information to be exported from one vendor to work on another, and sometimes it doesn't even work on the same product. So looking for a more preservation format for databases, we normally go to this amazing article from the National Archives of the UK about the properties that makes a good preservation format. It should have widespread use, a good support, be open standard format, good documentation, be stable, be easy to identify with all format identifiers, have a format validator, should not have patents or intellectual property constraints, should support metadata, should not be overly complex, should enable interoperability, should provide error detection facilities, and should be easy to reuse. And with that in mind, we, sorry, going forward and not back, if the system allows me to do so. So in our analysis, the format marks higher on all of those criteria is the CR format. It was specifically created to preserve databases. It is based on international standards. It focuses on preserving the database data, structure, and documenting the behavior. And it's a Swiss national standard and is now managed by the DILSIS board and the EU e-archiving building block. I will not say more about this as Kuldar Aas will talk more about this next session. So what I'd like to focus is what is the strategy here we are normally going for and using in production and supporting with our tools. So I would like to present you like two simple two database workflow archive flows, a simple and a more complex one. This one here is when you use a tool to migrate the format into a database, in the database plus some external related files into the CR preservation format. This file would then submit it to the archive, being it in the same institution or even on a different institution, where it would be validated against the specification plus other validations. So there is another, again, a new use for a tool here to validate the CR format against specifications, and add it to a catalog where end user will use it to the database viewer to inspect the content of the information that is within CR. Another more an alternative or more complete flow would include migrating the format into CR, but also creating documentation about the original application logic and interfaces, export the data in the original backup format, and possibly adding some finding aids to enrich the catalog. These will all need to be packed into a submission information package, if needed, of course, to be transferred into the archive, where it will be validated and added to a catalog or to a full digital preservation repository like Rhoda. The user will then use the catalog to find the database plus the documentation and alternative representations, and possibly using the database viewer to access the contents within the database. So there are here several things to unpack and several tools that we use in several of these parts. So for supporting these workflows, we provided here a set of open source tools that you can download and readily use on and see the documentation on databasepreservation.com. They are called the Database Preservation Toolkit. There are mainly three models of tools that work for different use cases. There is a desktop application to be able to use to save the database format, preservation format, validate it, and browse and search some of the content just to check if everything is there. There are some limitations here. There is the enterprise, which is a web application to browse and search on the content of multiple large preserved databases, and the developer, which is a command line tool and development library for automation and system integration. So I'm just going to show some of the top features of each of the tools. My computer is very slow with everything on. Sorry. So the desktop features, of course, there is desktop application for Windows, Mac OS, and Linux. It allows, when you open it, allows you to connect to database via GDBC connection and export the content into CR with several options along the way. It's a wizard that you go through several steps. You can connect to a local or remote and to test the connection, see helpful hints. There are optimized integrations with Microsoft Access, SQL Server, MySQL, MariaDB, Oracle, Postgres, Progress, OpenEdge, and Sybase. And there is a generic connection with JDBC, where you can add the driver and make the connection. It creates a migration report, a detailed report of all the changes and possible losses on the conversion, all the parameters for the export and selection, because you can select only a part of the database to export, are presented. All column data types, mappings to standard types are recorded, and all the compromises when extracting the information are documented. You can then edit the CR metadata, which is an important step for you to add metadata descriptions to the database, to the tables, to the columns, so you better understand its content. You can do a full validation against its specification, plus many additional checks for a thorough validation, including identity and relationship integrity. You can then use the desktop to directly browse and search database content with Google-like search and drill down to specific tables and using advanced search. So you don't need to use SQL to do this. And of course, there are other features like autoplate and so on. For the enterprise, the enterprise is a web application for enterprise architecture for large institutions with many databases and many users. So the system can be installed and scaled horizontally to support many very large databases being accessed by many users at the same time. You manage in a single system the several databases, and you can manage their status, enrich their metadata, validate them, make them ready for the users to search on them. You can do data transformation, so you can do denormalization within only with this viewer, so without changing the CR file. You can do column and table hiding to simplify the browsing and allow some anonymization of the content. The denormalization, with the denormalization, you can very easily take information that is sparse in several tables with relationships and bring it together into a single view or single table where the user can search through and relate several of the columns and get the response and export the content. It also supports single sign-on, so you can integrate this with your own authentication systems, and it supports internal authorization definition or configurable external authorization. With this, you can provide access direct to the users, to your transformed and simplified database, all documented, and through the web, and then allow them to directly search and export the content. The export features include extracting part of filtering the table and then exporting part of the content or all of the content into a format that can then be loaded into Microsoft Excel or any other spreadsheet format for easy analytics or diagrams. Also note that the desktop tool, although I didn't said, it also allows you to put CR back into a database. So that might be important to enable other kinds of situations. There is an activity log, who has done what and when and from where. This is a ISO 16363 certification requirement in terms of access of the content. And it supports multiple languages, including English, German, Estonian, Czech, and Portuguese. And searching systems, the Google-like system uses a stemming and stop words, which supports many other languages. The developer is our command line and Java library, normally used for automation of periodic preservation tasks, and allows you all to do system integration using it as a Java library. All of these is open source. The code base is open. You can also extend it for your own purposes and add new modules for import or export to support new or legacy data systems and other situations. There are many other features that are supported, including geodata from Oracle and selection and materialization of views, and automated quality assurance, which is a way for you to do get a hash or the protocol or the algorithm is called Merkle tree top hash, where you can get a single checksum hash for all the content within the database. The same procedure can be done via store procedure on the content, and then you can compare to see if you actually had everything, or use it to, because this is a blockchain-based technology, you can use it to ensure that the content or the archive was not changed in any way. There's also several information about features on the archive databases. So besides the features, I'd just like a couple of minutes to show you some real-world cases, the way we have used this. So one of the cases is a hospital that has a set of databases created to support specific hospital services, cardiothoracic, neonatology, and neutropenia, and they contain crucial information about the history of some patients that may be needed for urgent interventions. The databases were replaced by newer systems, but the information was never migrated to the newer systems, and it's needed because it's history of patients. So the original systems are obsolete, the submitters and developers are gone from the institution, and there's not enough documentation available. So the solution here was to export all information into CR. We did an expert analysis, kind of a reverse engineering of the application to be able to document and get all the information about the interface. We used Rhoda to keep the documentation, and the DBPTK Enterprise to provide access to the CR format. So we used data table and column management and data transformation to make it more user-friendly and better documented for the end user, which are the medics that need to access the documentation. And very quickly, another similar use case where you use this on the European Taxation and Customs Union for the New Year service, archiving the New Year service, which is a centralized interface with custom authorities for thousands of economic operators that bring goods to the European Union. So all transactions in the EU of goods will be recorded on this system by all member states, and transaction messages will need to be archived for a decade. So we estimate around 10 million messages per day, small XML files, and the production database needs to offload to the archive daily and purge the information. So we must ensure no message is lost or mangled during the archival process, and archive process must keep up with production. So the solution here was to do partial exports of the database into CR around one hour times, although this can be configurable. And we use a primary system to keep the CR files with some metadata, so Rhoda. And then when you need to access, and every CR has millions of messages, and when you need to access a certain message, you need to first load the whole CR into the database provision toolkit enterprise, and then access the message and then retrieve the original messages there. So quality assurance here is key, and this is why we use the Merkle tree top hash algorithm to check if what we have archived is the same that is on the database before it is deleted on the database. And I hope I didn't take too much time, and I'm open to any questions or comments.
I'm extent happy that I'm not going to talk too much about CR. So maybe even surprisingly little. So I'm talking about E-ARK standardization for databases, but the stress in my presentation is really on the standardization. What we do in regard to standardization, and less about what exactly we do about CR. But let's get going. And Kai, you asked everybody to also introduce themselves a little bit. So my name is Kuldar Aas. I'm from the National Archives of Estonia, and next March will be my 20 years in digital preservation. So 20 years ago in 2002, I started with exactly the same topic, so the preservation of databases, and started looking into my first few FoxPro databases to archive. So that's my background. But before getting to standardization, just one slide also on E-ARK. So I suppose the keyword E-ARK is to some extent known to all of you. But just to explain a little bit what it is, it might be a little bit surprising for you that E-ARK as a specific entity doesn't really exist. So the brand E-ARK is coming actually from a series of European Commission funded projects. So there was the initial E-ARK project in 2014 to 2017. Then we had the E-ARK for All one-year project between 2018 and 19. And now we are just finishing off the third project called E-ARK 3. So that's a 2-year project that we started in 2019, and that's now running into October 2021. Actually, the even more important words and the established entities next to E-ARK are the e-archiving building block, first off, which is then the European Commission owned building block that aims to support interoperability in digital archiving. So that's something that the European Commission aims. And indeed, as I said, it's you can see it also on the slide. The aim of the e-archiving building block is to facilitate the preservation, migration, reuse, and trust of your data. There we have Commission employees, Commission staff to be the business owners and to make all the decisions of what are the directions. So it's kind of a central thing, central interoperability thing at the European Commission. Next to the e-archiving building block, there are, for example, building blocks or e-invoicing, e-delivery, e-signatures, e-ID, etc. And now the relation between E-ARK and e-archiving is that E-ARK, and more specifically the current E-ARK 3 project, is the service provider for the building block. So again, the European Commission is the owner. Nice people in the secretariats there are then leading the building block, and the ones who are executing are then people like me and Louise within this E-ARK project. And the third thing on this slide that is also connected to E-ARK is the Digital Information Lifecycle Interoperability Standards Board, or more as an abbreviation, the DILSIS board, which then has the task of maintaining the specifications developed in previous E-ARK projects plus CEART. So that's as a context here. And also to mention here the vision of E-ARK as we first developed it in 2014 with the first E-ARK project is that the whole thing about E-ARK is to work on interoperability. So we all know that there are many problems associated with digitalization in general, and we also know that far too often different countries and different directors and different software providers implement different kinds of principles and different standards. So the level of fragmentation in the field of digitalization is actually far too much, and that also is a problem in regard to collaboration and reuse of tools and best practices. And that's exactly what we have been working on with within E-ARK and within the people and organizations behind E-ARK for the past 7 years or even more. So what is the point about E-ARK and databases? So the initial authors of the idea of E-ARK, so we started discussing that among a set of national archives. So the whole question about interoperability and how we have one set of tools in Estonia and another set of tools in Slovenia and Denmark. So that was around 2011, 2012 when we first started developing the idea, and when we with the same bunch of people, so mainly the national archives people, we also started looking for the technical institutions to join us, the scientific institutions to join us, and we also went on to lobby with the European Commission to get some funding. But the whole legacy of national archives means that the focus of the E-ARK initiatives and also the E-ARK building block is still very much with records in the widest sense. So, you know, a record in the meaning of archiving is any kind of information that has legal value and is authentic, etc. And that is very much then in two sources. That is content in relational databases, and that is content in records management systems, or records management more broadly. So these are still the two most important data types for E-ARK initiatives, therefore. Just to give you an example on the Estonian National Archives, the situation, or the kind of the problem we have to deal with, is that in the whole public sector of Estonia, we have over 1,300 registered public sector information systems. So Estonia is small. We are quite centralized. So I would think that in Germany and in UK, France, etc., you have really thousands of relational databases in the public sector. Then also in Estonia, there was one survey a few years ago, which found out that about 95% of these public records are assumed to be relational data. So while everybody is thinking about records still in the sense of paper records and PDF files and doc files, then actually the public sector, the whole government, and also the municipalities are creating much of their records as relational data into relational databases. Obviously, not all of that is of archival value, but still we are talking here about hundreds of databases of archival value. So in Estonia, more precisely, our latest appraisal decision was that we have 112 archival value databases, which we are dealing with, which are actively capturing archiving regularly. And obviously, there are all kinds of different platforms present. So there is Oracle, there is MySQL, MS SQL, FoxPro was already mentioned as one of the legacy systems being used in the old times. So it's really what we need is a universal, simple, standardized preservation format, which we can use to really connect to all kinds of these different databases, and both preserve the data itself, as well also the service definitions, as we like to call it. So in the end of the day, the database is often or mostly hidden from the users. What the users see is some kind of a public service, a view, a query. So these are essential bits that we need to preserve. So getting back to DILSIS, then also to note that that in the DILSIS, the Digital Information Lifecycle Interoperability Standards Board, the standardization is not only about CEART. So CEART is just one of the components that we are looking into among quite a few others. So E-ARK also offers, or the E-ARK building block also offers the generic information package specifications, the SIP, PDIP of E-ARK. But then, yeah, we have the CEART, ERMS, geodata. Now, quite recently, we also developed eHealth specifications, also specifications for archival descriptions and premise. So it's quite a huge set of different standards, or yeah, not really standards, but certifications we maintain. And basically, each of these specifications gets some level of support from the DILSIS board and from the E-ARK building block. And the support comes in quite a few different ways. So for all the standards that we maintain, including then also CEART, we have developed some guidelines and procedures. So how to maintain specifications, how to review them, how to develop, how to add new issues, comments. We have created then internet presence or web presence for all of these. So there are dedicated landing pages for all specifications. And when you go to dilsis.eu/content types/CEART, then that's a dedicated page for CEART specification. Within the DILSIS board, we also organize open reviews. So the CEART 2.2 version 2.2 request for comments was open between October 2020 and January 2021. And in the end of the day, we also aim to have all the development as open as possible. So actually the specs themselves and also the issue handling and all the work on the next versions of the verifications is happening on GitHub. So for example, you go to github.com/dilsisport/CEART, And if you have something you don't like about CEARC, then you can leave your comments there, and we will look into it. Now, E-ARK itself, we wouldn't really say that E-ARK is maintaining the specifications as such, but rather our point of view is that we are supporting everybody else who wants to work with one or the other specification. And CEARK is here a good example, because that's not something we developed, but that's really coming from the Swiss Federal Archives. And with E-ARK and the Swiss Federal Archives have been working together since 2017 or 2016, 2017, but the version 2.0 came out, and now obviously there was also the 2.1.1 and 2.2, so the version 2.2 being released in the end of August this year. And our idea is quite simple. So we see that the more people we get to work together on specifications, the more errors and issues we can find, the more knowledge we can pour into the specification development. So really our aim in E-ARK, or the E-ARK building block, or the DLC support, is to make it as comfortable for people to join into the development, and to give them the possibility to discuss and to work, and then just monitor and hope that all the good ideas are being incorporated in consecutive versions of the specification. And the main concern, so we talked before about the issue of CEARK, and obviously the most crucial issue that was present in version 1.0 was the scalability. And now through the 2.0, 2.1, 2.2, especially the E-ARK members from Denmark and Estonia have been looking into how to solve that, and we have added more and more ways on how to include support for lobes outside CEARK, so how to get the bulk of the data outside of the XML files, which indeed are hard to manage on large-scale databases. So that has been one of the key focus until now. But as I said, it's effectively in E-ARK, we want to facilitate you working and not necessarily pushing only on our own ideas. However, there is more. So before my presentation, Louise also mentioned that there is not just CEARK, but when you are talking about a database transfer to a national archives or any digital archive, then it's usually much more. So for example, in Estonia, we archive also the original dump, and if possible, some code of the application. So if there is a good way of doing emulation in future, then it could also, we wouldn't bury that way. We usually have some additional metadata in Dublin Core or EAD, even more as a national archives. We have a lot of documentation we want to gather. So as we are losing still much of the original application layer, then we are trying to gather as much of the documentation. We want to do videos about the original environment, how the system was used, so that kind of also the IT archivists in future might get a little bit of a look and feel of the database. And for all of this, what we have next to CEARK in DLCs is what we call SITS CEARK. And that is basically quite a lightweight specification that proposes one way of packaging a CEARK snapshot with potential other components. So as mentioned, the original dump, the additional metadata documentation into a nice and neat information package you can transfer to the National Archives or your digital archive. So that's a first version, again released in August 31st, version 1.0. Really like to see all of you looking at it and providing your comments. And also beyond that, I see the slide is a bit weird here, but I hope you will get the slides afterwards and it will look nicer there. The creation of a CEARK snapshot is just a part of the whole workflow of archiving database. Here, what you have on the example is the workflow of the Estonian National Archives, and basically the small parts highlighted there is the creation of the CEART file. There are many other steps about gathering documentation, looking into which parts exactly are necessary to be archived. So in most cases, we don't necessarily want to archive it in 20 terabyte database as a CEART snapshot, but we are going into it if the agency has the competence and we are looking at the data, which tables are worth of archiving. Are there maybe only some of the views that are necessary to be archived, so we can materialize some views and get rid of the old relational database. So there are all kinds of these questions. Validation and quality control. Again, it's in our case, it's a process which is quite extensively outside of the DBPTK that we are using in Estonia. So DBPTK, in the end of the day, as also CEART suite, as also Spectral Core, all of these are tools that are doing a piece of this job. But in the end of the day, the whole process of archiving databases is much, much wider. And that is something that we also want to achieve in E-ARK. And I hope that many of you received quite recently an invitation or an announcement that you have been added into a relational database archiving interest group mailing list, or RDB-AIG mailing list. So that's something that we in E-ARK established in September, and that we hope it's this place where all of us can also share our ideas about and our experiences on how we use the tools, what are the problems with the specifications, etc. So yeah, that's it. Separate slide here. Relational database archiving interest group. List being available. You can see the owners currently from the National Archives of Estonia and the Danish National Archives, but all of you are welcome to join this after this workshop. If you want to have any follow-up questions, feel free to use our list. We want to make the moderation as low level as possible. So really all your ideas on how you use CEART, how you use CEART, how you use your tools, what are your best practices also beyond CEART, all of this is very, very welcome on this. So to wrap up, in the end of the day, yeah, so maybe it's time to get used to not using E-ARK when talking about our work, but really to use the word TILSIS. That is the specification maintenance board we have set up with quite a few of the National Archives and with support from the European Commission that we use also for lobbying the European Commission and talking to them about what are the needs in the community. What I want to tell you is that really all the TILSIS work and also the E-ARK work, our mindset is about being open and inclusive. All of you are welcome to join the work, especially in regard to CEART. We know very well that CEART has its problems, but that's precisely the reason why we want to hear your opinions and ideas, and especially technical proposals on how to improve it. The current leads of the CEART group are Danish National Archives and the Swiss Federal Archives. So these are the two that should be contacted. And we are hoping on all of you to also improve the communication. So when I mentioned the CEART review in early 2021, so the version 2.2 request for comments, then the feedback we got was a total of 3 responses, and that's obviously our big failure. Seeing that we have here almost 50 people in today's workshop, then I would think that at least 30 or 40 responses to such an important development would be reasonable, but I suppose we just didn't get to you and we didn't send the messages about the review being open to the right places. So it's also thank you to Kai for giving us the opportunity to also mention and talk about TILSIS and the E-ARK effort. And we hope that you will you will note our work and come forward to also participate in that. And yeah, in the end of the day, the most important message is that from E-ARK side, we are happy to help you to work together, and obviously to also use our European Commission connections to lobby for any kind of funding, any good ideas that we develop in regard to updating CArch or updating any of the tools, commonly developing common libraries, code libraries for CArch support. That's all very much welcome. But I'll finish here and looking forward to all of your questions.